Good morning, everyone. Is it working? Yeah, it's on. Okay. Thank you for coming. I think there are more people than I expected because maybe yesterday people might have some night in Amsterdam. Okay. Thanks for coming. My name is Jung, and I'm a master's student in Stony Brook University, and I'm also in a team called 아재들. And before I begin, I would like to introduce my team. It's called 아재들, and it means guys who act like old people in Korean. And we mainly work for researching on malwares and rootkits. And I would like to thank them for having me here to present the works, and also my advisor in Stony Brook. And you can send me an email if you have any questions or feedbacks. And also, I thank the HITV board members and the staffs for having me presentation here. Yeah, let's begin. These are the contents of tables of contents: introduction, explanation, result, conclusion, and Q&A. When we think of hiding tasks, we mainly think of rootkits and malwares, right? But let's don't think about this today. We focused on researching, finding some unused features that are still remaining on computers. And to do that, we found out something called task switching method. Maybe everybody knows what task switching is. It's something to make the computer look like multitasking. So, yeah, computers are so fast that if you switch tasks, it looks like they're working at the same time. That's what we know about the task switching. And let's go a little bit deeper inside. There are two types of task switching methods, and the first one is the hardware task switching, and the second one is the software task switching. And the first one, the hardware task switching, it was used until only the Windows 3.1, which I think I was born around that time, and it's used for 32 bits. And it uses the structures defined by the CPU manufacturers, and it access to the CPU directly. But in other words, for the software task switching, it is used until today, and it's for the 64 bits. And OS, this structure is defined by the OS, and it does not directly access to the CPU. However, the OS itself manages everything about the task switching and about the management of the computer. So to summarize, what I want to say is that hardware task switching is something not used today, but still remaining. And software task switching is something we are using today. So one question, then do you think the hardware task switching disappeared? Yeah, the answer is no. It's because of the compatibility the CPU should have, because there's still lots of people using the 32-bit computers. So we are focusing on this fact that we are not using this feature. Yes, we are trying to use hardware task switching with the software task switching. I know it's quite hard to understand. I will explain more about it. You can see on the right side, it is said software task switching, and on the left side, it's called the hardware task switching. Currently, it's like in the red box. We use this as the software task switching, but what we're trying to do is we're trying to manually operate the hardware task switching, like this. If this happens, what's so cool about this is that I told you guys that OS operates everything and manages everything. But if the hardware test switching happens, OS won't be able to notice anything about the task running inside the hardware test switching. And to manually operate the hardware test switching, we need to achieve the ring zero authority. To do that, we install the driver. And after achieving the ring zero, we modify the global descriptor table and test state segments. And then if we have that, we can use our own task for the hardware test switching. I know it's hard to understand, so I prepared a video. In the screen, you might see some kind of events happening, and just think this as the normal user's perspective for the computer. You're eating a French fries, and look at the beer over here, and you can see the beer disappeared. What this shows is that OS doesn't know what happens when the hardware test switching happens, just like the beer disappeared. French fries, we know who did it, but the beer, we don't know who stole the beer. That's what we're trying to do. And of course, stealing the beer itself is too noticeable. So what if we do something unnoticeable, like stealing CPU resources? That's what we thought of. And that's the basic concept of our research. And I quite spent a lot of time explaining about our concept. Let's go a little bit deep into the hardware test switching method. I will start with the terminology. Inside the global descriptor table, there are lots of information about systems, but we're trying to use one of those called TSS descriptor. TSS descriptor is something that shows the information, the address of the TSS. What TSS is called task state segment. It is defined by the CPU manufacturers, and it saves the states of the task. And with this information or states, the CPU uses this TSS information to operate the task. And we can say that TSS, each task has one TSS, no more or no less than that. One task should have one TSS. And what we are trying to do is we created our own TSS called my TSS, and we made TSS descriptor 2 here to point this address. And when we trigger the jump or call instruction, it will automatically switch the TSS to my TSS to operate our own task. Yeah, if we trigger, it will go to my task. If we just finish our task, it goes back to the normal task. That's what we're trying to do here. Yeah, the previous figures were just for explanation. In the real world, in Windows, there are a total of 4 TSSs. In Linux, there are 2 TSSs. And if it is stated as busy, then it means that that particular TSS is being used. And the rest of them will be stated as available. And our team modified the second one over there, 51 and the 31st one. We are trying to modify that TSS to look like this. We will use that TSS descriptor to show it busy. And whenever we operate the hardware test switching, it will simply change to like this: busy, available, busy, available. Yeah, this was the explanation. And I will show you the result, what we have done. Maybe it might not be so easy to understand. It's much better to see some results. The descriptor over there at the first, uh, which is written busy, that's the normal task. And the task is printing before task switching. And my TSS, at the second, it prints out, show me the AJD. And just like I said, if I trigger the jump or call instruction, it will automatically switch to my TSS to operate our task like this. And if once it's done, it will go back to the normal TSS to print out this kind of things. It's the simple hardware task switching method. And we have done this in Windows and Linux, and we succeeded it. I know it's hard, so I prepared another demo video of this. It's XP, it's so old, right? On the left side, you can see some program called install driver. And we install our own driver to achieve the ring 0. And once we get it, the driver modifies the GDT and TSS, and it also has our task in it. On the right side, it is called the Windows debugger, and it will automatically print out what the task is doing inside the driver. And there are 2 tasks in the driver now for the demo. The first one is just the normal task, which the OS can see. And it will just print out function calling for 2,000 lines. And then it will automatically switch to hardware task switching. And it will show task switching for 2,000 lines again. According to what I said in the beginning, since the OS doesn't care about what hardware task switching is doing, in the task management, it won't display any CPU usages or the process ID. I think it's much better to watch. Here, I start and function calling, which I said it was the normal task. You can see that the CPU goes up to like 60, but once it reaches 2000, it switches to the hardware task switching, and you can see that it's like almost 1 to 4 CPU usages. And once it reaches 2,000 lines, it will automatically go back to the normal task again, and it will print out again the 60% CPU usages. The reason why I use the task management is because from the normal user perspective, people doesn't know, when they think their computer is suspicious, they try to see what's wrong with the computer, and they use the task management to see what process is going on or whether the CPU usage is too much. That's why we use the task management to check it. And after this video is showing that hardware manually operating the hardware task switching is working. So we try to also use the detection tools like malware tools or rootkit tools to see if they can detect our modification of GDT and TSS. And the result was that we tried many tools, but none of those found our modification. Yeah, and this shows that there's no detection tool there's currently no techniques that detects the modification of GDT or the TSS. And back to our basic idea. The previous slides were to show that manually operating the hardware system works. But now what we are trying to do is, what if the hardware scheduler and the OS scheduler works at the same time? What if it coexists at the real world? So we had an experiment of having OS and the hardware scheduler be at the same time. What we were trying to do is how the task of hardware switching affects the OS scheduler by measuring the normal task in OS. Yeah, the graph is quite dirty. I will explain one by one. I told you that we are going to measure the time of the normal task, right, in the OS. And at the same time, we will execute another task using the hardware task switching for 10 cases like this. And each cases, we will increase the CPU utilization. That CPU utilization is from the hardware task switching task. If you increase the lines of printed lines, then the CPU utilization will go up. Like this. And for the normal task in OS, we made it to use only 55% of the CPU usages. That means the user will see only the 55% in the task management. However, the actual CPU, required CPU is the sum of the task in hardware task switching and the OS. So we add those together. If you take a look at the line 50, you can see that it goes above 100. What happens if CPU usage goes above 100? It stops, right? So we try to measure this in using the online timer. You can see that if the sum of the CPU utilization goes above 100, previously it was almost similar, but now it goes high and high and high. So this means the user has to wait for that long with only 55% of CPU usage. Yeah, because maybe the required CPU utilization is above 100%. And if the user waits, user will think that the computer is suspicious because it's becoming so slow, even though they are using only the 55% task. And when you think it's suspicious, they will check their computer using the detection tools or the task management. And of course, they cannot detect it, but from the attacker point of view, it's the best if they don't know what you're doing. So that's why I mentioned this. And one more thing to tell you, I measured the time with online timer and the OS timer, but you can see that the OS timer is almost similar till the end. What this shows is that actual time, it takes like 70 seconds, but at the end, OS timer is the same as the first one. What this shows is that OS timer stops during the hardware task is occurring. And I think this is quite a big problem. And this is the line graph of the time difference. This is the OS timer, and this is the online timer. You can see that it's quite big difference. Yeah, this is what the user should think, that the task should be taking time, but actually it's taking this much. Yes, and to the conclusion, there are like 3 problems it can lead to. The first one is that it gives the chance to the attackers. Let's say that using the previous example, the normal users use 50, let's say they are using 55%. That means the attackers have like 45% to use to attack. their computers. What if it intrudes the servers or make zombie PCs using minor CPU usages? Then you might be able to use it as the mining, which is very hot these days. Of course, we didn't do it because it's too difficult, but I would love to do that. And the second problem is the belief in OS. Everybody thinks that the OS is reliable, but with the hardware task switching, it won't be reliable anymore because the event log and the time from the OS won't be trustful anymore. And inside the investigation using the forensics, I think this is a big problem. And the most big problem is the ring zero. Manually working the hardware task switching was possible because of the ring zero. Without the ring zero authority, you might not be able to operate the hardware task switching manually. So what our team hoped was to reduce the power of the authority of the ring zero. And the limitations, it's only for the 32-bit yet, but what I can say that is that there's still many people using 32 bits. Of course, compared to 64 bits, they're very little, but the absolute number of computers using 32 bits, there's still a lot out there. And our team is currently working on 64 bits as well. And hopefully, I hope we can present it in Singapore in a couple of months. And second, it can be detected if you scan the memory. But what I want to say is that normal users don't know, they're not experts like you guys, so they don't know how to scan the memories to find these malicious tasks. What the normal users do is just to use the detection tools or the task management to see what it is wrong, or yeah. So from the attacker point of view, if you don't make it suspicious, like from the previous example, if the user is using 55%, what if the attacker uses less than 45? Then there's no way the user knows about these attacks. So how would you scan the memory to find malicious task if you don't know it is suspicious or not? That's what I think. And last is the contribution. First, I think we found a new approach of hiding tasks. And second, this can lead to potential dangers in the future, like such as accessing the files, networks, and CPU. And the third, we showed that ring zero is powerful, much powerful than we think. And that's it. Actually, this presentation was my first conference presentation in my whole life, and it was quite nervous, but I hope you liked it. Yeah, thank you.
Well done, Kyeong. And maybe you're also ready for the first questions you've ever had after
Yeah.
a presentation?
Yeah, sure.
Okay,
Of
anybody
course.
got questions for him?
Yeah,
Yeah.
feel free to.
So my question is about your results, because you did the test both on Windows and Linux machine, but you didn't show the Linux results.
Oh, we thought because...
Is it the same?
Yeah, it's the same.
Okay.
That was a good question.
Any other questions? Yes, here.
On multi-core or SMP systems, there are multiple hardware tasks active at the same time, right?
Yeah, that's a great question. Our research was for just one core, not the multi-core.
Okay, because on a multi-core system,
Yeah,
if there are
of-
multiple hardware tasks, and maybe
Yes.
one of yours could still be running while the operating system is running. But it would be
Yes.
interesting to see what kind of, what that does to the OS timers and everything.
Oh,
Because the OS timer, I mean, if it stops here on a single core, what happens on multi-core, right?
We haven't tried it on the multi-core, but I think after the 64-bit is done, I think we will do that as the next
Right.
research.
Thank you.
Thank you.
Any more questions from the audience? Okay, no. Then I'd like to thank you very much for your first talk.
Thank you.